Our next lab is motion in an inclined plane, and the final goal of this lab is to calculate acceleration due to gravity using experimental data. Uh, an inclined plane is a mechanical tool that allows an object to move between different heights. You can either lower the height or increase the height of an object, and when we are doing it, we generally use inclined plane. But for example, we can see here by placing an object on a ramp, we can essentially slow down its downward motion compared to a straight vertical drop. So, for example, if we are dropping the object's height from higher position to lower position, if we were to just drop from a vertical, it will uh, drop under acceleration due to gravity of 9.8 meter per second square, whereas if we use a ramp, uh, only the component, this force component acts in the downward direction, which essentially slows down its downward motion compared to a straight vertical drop. So in this kind of cases, we use a ramp to sorry we use a ramp to lower or increase the height of an object. And in this lab, we will first want to investigate relationship between angle of inclination and the resulting acceleration. In this case, this is acceleration along the plane, but not the acceleration due to gravity, because remember, acceleration due to gravity, we generally represent it with letter G, is a constant, and it's around 9.8 meter per second square, but for simplicity we generally use 10 meter per second square. So first we will establish we will investigate relationship between angle of inclination and the resulting acceleration of the object along the plane, and then we will also determine the effect of mass on both the net force and the acceleration along that plane. So we can also tune the mass and determine the effect of mass on the net force and acceleration, and at the and then again we can also study the force resolution. We did an lab in we already went through vector lab where we studied how to determine the components of a vector force. We will again do the same here and practice identifying components along two orthogonal axes. In this case, one along the one parallel to the surface of inclination, surface of inclined plane, and another perpendicular to that inclined plane. And finally we will collect some data and use that data to calculate the acceleration due to gravity and compare this with uh, standard acceleration due to gravity, and calculate the error between the standard acceleration due to gravity and the acceleration due to gravity uses calculated using the simulation. Before we start the lab, first let's look at some uh, basics about the lab. So first, we already been through this here. Let's look at it again. So let's say this is an object we are interested in, and it has a mass of m. then because of the gravity from Earth, this object experiences force because of the acceleration due to gravity, and that is called the weight, and it's given by mass times acceleration due to gravity. And this force always acts perpendicular toward the Earth's surface. So this particle force is mg. And now if we have a force, we can always resolve into components, and in this case we will resolve this force along two axes, one parallel to the surface, another perpendicular to the surface. And if we were to resolve this force, and since this angle is theta, the component along the plane will be mg sine theta, and the component that's perpendicular to the surface will be mg cosine theta. And this mg cosine theta force is going into the surface, into the surface here. And when two objects are touching, we'll also have a normal force, and that is going from opposite to this component. So this normal force and this force are balanced by each other and doesn't have any uh, effect on acceleration along the surface. So whenever this object is sliding along this surface, the only component that creates this acceleration is because of mg sine theta. But remember, there is always friction, and friction acts in opposite direction to the motion. However, in this lab, we will consider that the surface is frictionless, and we will just assume that there's no friction, so we will ignore this friction component, as well as we will also consider there's no air resistance. So we are doing this experiment considering it's an ideal case where there's no air resistance and no friction between the object and the inclined plane. And we know from the kinetic equation that the distance covered by an object with an initial velocity of v naught, uh, v naught within a time interval t, we can, and acceleration due to gravity g, we know this relationship, where we can calculate the distance using all this information, distance covered using all this information. Here here v naught is initial velocity, t is time, g is acceleration due to gravity, and t square is basically time squared. So we will use this information to calculate g. And we will use this information to calculate g, and we will also calculate g using this trigonometric relationship from here. So if this component is what causing the acceleration along the surface, we can establish a relationship here. G is equals to a sine theta, and here this a is acceleration along the plane, and g is acceleration due to gravity. So these two accelerations are completely a different thing, and in other word, a is the component of this g along the surface of the incline. And again, remember that we are assuming there's no friction between the surface and the object, uh, and there's no air resistance. So basically we will use these two formulas from the diagram, established from the diagram and kinetic equation, to calculate acceleration due to gravity using the motion in inclined plane, as well as a vertical free fall. So first we the simulation we will be using is from the physics classroom. And in order to open this lab, first I have provided the link here. You can open this, and you will see this page here. So when we said we will consider acceleration, sorry, the friction to be 0, we will, what we are saying is we will set this friction value to 0. So you have to set this both coefficient of kinetic friction as well as coefficient of static friction to 0. You can also observe that when I have set some coefficient, you can see the surface is rough, and when you bring it back to 0, now the surface of the ramp is very smooth. And let's look at the interface here. In order to change the angle of ramp, you can just click and drag it here like this. So you can change the angle, or you can also change using the slider here. So you can either click and drag to whatever angle you want, or you can use the slider. You can also change the mass of the object, and you can also show all the force components here, forces, or if you want you can also look at the component here, perpendicular component fg cosine theta, and parallel component fg sine theta. And you can even look at the values here like this, and you can start your simulation. It will start going down like this, and it will show all the force component here. And one more thing you can look at is motion. So if you look at here, this is x, so this is the position, how much it has traveled, and then this is the velocity. The velocity from this position to this position, you can see it was gradually increasing because it was at constant acceleration here. Because if you remember, it's accelerated because of mg sine theta, and theta is constant, m is constant, g is also constant. So the acceleration is basically mg, established from that relation, g sine theta. So we can look at here and figure out that the acceleration is constant. And also if you look at here, acceleration here is between 0 and 10, so it's somewhere between 5 meter per second square. Now if you go back to our table, our value here, the acceleration here is the acceleration shown here, acceleration shown in this motion graph here, in this graph, and g is what we will calculate. Now we know how the interface looks like, and what we can easily turn this informations on and off just by clicking. And if you want to reset everything, you can just click on reset and then bring this slider back to 0, and now we have it. We can also not just inclined plane, but we can also, if we make this angle at 90 degree, we can also make it a vertical free fall. We'll use that in the second part of the lab. Now we know about the interface, and the link is provided here. We can start our lab, and the first section, in the first section of the lab, you will do 4 trial, and you will change angle between 10 to 45 degree, and you will keep the mass at 1 kg and friction at 0. So basically friction at 0, both static and kinetic, and then mass at 1, and your angle should be between 10 to 40. You can show forces, components, values, and motion, and then you will start the simulation. You will approximate your acceleration here. Previously it was around in the center, so we said acceleration along the plane was 5. Now if you look at here, this is from 0 to 10, so it's around I will say 3 meter per second square. So you will make an approximation from here. uh, oh here, if you reset here, and if you click on motion, as well as instead of motion, if you show on calculation, force, component, and start. Sorry, it's not showing the acceleration. I thought it used to show acceleration. So basically use this motion and approximate okay, if you remember, when I did this, the acceleration is shown here. You can use this acceleration. Oh, it's still 5 meter per second square. So the acceleration is 5 meter per second square. Then what was the angle? Angle is 30. Then you will calculate sine theta. You will use acceleration from here, and then calculate g using these 3 information and this formula. And in the second part of the lab, instead of instead of using angle between 10 to 20, we'll use 90-degree angle, which basically creates a free fall. Since there's no friction and air resistance, basically this object will fall under gravity, and we call this kind of fall free fall. We'll use this information to calculate acceleration due to gravity using kinetic relation shown here. In this formula, we can change this formula to this simplified formula. Because there's no initial acceleration, we can simply ignore v naught t term and change that equation to this equation, where this d is the distance covered by the object. In this scenario, that will be 0.6 meter. Now for the second section, go here, change the angle to 0, angle to 90, friction to 0. Now we have a free body. Also remember, we were doing all our lab at lab with 1 kg mass. Now if you for this lab, one more thing you have to do is use a stopwatch to calculate the to measure the time taken for object to fall from this position to this position. I will recommend you to use a mobile phone instead of computer computer clock, because when you click in one section, it will just go in the background. Or if you have a big screen, you can use multiple screen and just use like this. Now let's for the second section, use like this. Start the clock, and so this is second, right? So this is 0.5.31. It took around 5.31 seconds to drop from this position to this position, and you will use that time and put it here. You will change mass to different values, and then using this formula, you will calculate acceleration due to gravity g. And once you calculate all this 1 2 3 4 5 different values, you will calculate the average of this 5g. So average is basically, you will sum all of this and then divide by number of data points, in this case 5. And then you will calculate the error between your calculated acceleration due to gravity to standard gravity, and give your answer here. And then you will just save the PDF and submit it on the canvas.